We're recording.
Okay, thanks for coming for this seminar. I'd like to introduce Professor Srdjan Capkun from ETH Zurich, which is also called Federal Institute of Technology. Professor Capkun has a very large research group in Zurich with another faculty, almost 30 PhD students. He just organized a workshop on wireless security in the month of September or October. And to give you a background, Professor Srdjan graduated from Federal Institute of Technology in Lausanne. It's also called EPFL. And his PhD thesis was done with Professor Huba, he's one of the leaders in networking. Professor Capkun has got his undergraduate degree in Croatia, University of Split, and he has also worked in UCLA and also in the Technical University of Denmark. And we are very delighted to have him here. And I think you're going to learn something and as well as remember him for a long time. Hope he comes back again. Thank you for coming.
Thank you, Bharat, for this very nice introduction. So thank you for this very nice introduction. So the topic that I'll be covering today is about securing navigation, or better say securing localization, and also time synchronization in wireless networks. And I'll show how securing navigation can also help in securing some basic, in setting up some basic security services in wireless networks. So we do live in an age of wireless communications, and we are probably in the future going to live in a more, let's say, surrounded by even more wireless networks, from robot networks to vehicular networks, sensor networks. All these wireless networks will be around us. So we will effectively digitalize our physical world. There will be a lot of sensing, and there will be a lot of communication, mobile wireless devices running around us, or we will run around carrying those kind of devices. So a kind of a catchphrase there is also an Internet of Things, right? So from RFIDs to vehicular networks. So in those kind of networks, the importance of location information is very crucial. So what changes when you go mobile from a fixed computer that you place in your office? Well, what changes is that the location of this device changes all the time. I mean, you go mobile, so the location of your device changes all the time. And you can leverage on that, and as it was shown through many years of research now, that you can leverage on mobility, and we can, through knowledge of location, we can gain a lot. So in terms of security, there are a number of applications that can benefit from obtaining a correct information, or better say a secure information about the location of a given device. Equally applies, the same thing applies to time, but here there are some applications that can benefit from this information about the location of the devices, especially if you have safety critical applications, or if you want to protect some infrastructures. Well, if you place the sensor somewhere, you want to know where that sensor is at all times. You want to know if someone moved it, and you want to be able to verify if someone is claiming to be at a given location that he is actually there. So because of the large importance of location, many terrestrial and global navigation systems have emerged, and obviously GPS is the most prominent one. So we use a set of satellites emitting certain signals that we pick up on the surface of the Earth, and we obtain our location through that. So that's satellite localization that most of us are pretty familiar with. There are a number of terrestrial localization systems, namely developed to enable indoor localization, and also to enable localization in some sort of ad hoc scenarios where either the satellites are not available, or where where the signals of the satellites cannot be received, or are, for example, jammed. One can also extend localization to multi-hop scenarios. So there are many research papers and commercial systems available today, either based on received signal strength or time of flight or time difference of arrival that will give you your location, provided that you install a certain infrastructure in the buildings or for example, on a university campus. So there are many localization systems, but people haven't really looked at the security issues there. So they haven't really looked at the vulnerabilities of these localization systems. And this is what I'm going to go briefly through, and then I'll show you one example, or better say, few examples, given time, of secure localization systems. So what are the problems here? Well, if you take GPS, for example, everyone would say, well, this is a very nice system, it's very well built, it's designed to provide us with a location. We have these satellites which are sending certain signals, right? And we compute the ranges to the satellites, or better say pseudo ranges, and then based on some calculation we are going to compute our location. But these signals are not authenticated, so they can be reproduced, they can be replayed at a different location, and they can be, for example, delayed. So the reason for this, so an attacker can essentially introduce a delay of the signal received at your device. And when he reduces a delay of a signal received at your device, you will obtain an incorrect location. Your computed location will be somewhere else. And this is not just fiction, right? I mean, there are well documented, and I'll show that later, attacks on GPS that work in that way. So there are many attacks that one can do. You can manipulate the ranges, you can replay the signals, you can delay the signals, you can simply block the legitimate signals and generate your own signals. It is very easy to do that. GPS signals are very weak, right? They are extremely weak, 10 to the power of minus 15 watts. So you can easily overshadow them with something else. The codes that are used there are known, so you can simply overshadow the signal, and the signal the original signal will appear as noise in the attacker's signal. So the delay is pretty easy, right? You can fake a location of a device as you wish. So instead of obtaining its true location, well, the device will obtain a different location, a spoofed location, P prime. And the device doesn't know what happened, right? I mean, it's only receiving the signals and computing its location. So there are many examples how this can be done. You can buy a GPS satellite simulator and just get closer to a device with this simulator than the satellites are. Obviously, you are much closer. You can use a much higher power. You can overshadow the signals, and there you go, right? You can spoof any location. Instead of your device showing that you are here in West Lafayette, you would, for example, it would be indicating that you are in Hawaii or somewhere else. Maybe you want to be there, but you are in fact not there. So, and someone is trying to convince you that you are. Now, if you take an example of a robot which cannot have such ability to estimate where it actually is, or to do some deduction, then you can do quite a lot. Well, there are certainly more aggressive ways of doing denial of service attacks on satellites, right? You can just shoot them down, as China recently did as a test, right? You can launch a projectile and you can just kill GPS. So that's another argument why we need a more robust terrestrial localization systems, because we need an alternative, right? I mean, you cannot just keep on launching satellites. It's not as easy as setting up some terrestrial mobile localization system. And you can easily, obviously, jam, right? I mean, there are many examples of jamming GPS. Even military GPS can be easily jammed because of such a weak strength of their signals. But it's not only about GPS. So GPS is just an illustrative example that's probably known to all of us, right? But if you take a closer look at any type of localization system, be it time difference of arrival based, be it received signal strength based, being some plain multilateration or beacon based, you have the same problem, right? Someone can replay the beacons that he picked up at one location to another location. So a device that's located here will hear these three beacons and will believe that it is in this red triangle over there. So it's very easy, right? It's a simple replay attack. Here as well, in time of arrival based localization, you can do exactly the same as was done with GPS. With time difference of arrival systems, you can cheat using either directional antennas or any other way. Obviously, for different attacks, you need different levels of sophistication in terms of the equipment that you have, but they are fairly possible. Especially, for example, in ultrasonic based systems, they are fairly vulnerable to many attacks. So why isn't it enough just to say, well, let's encrypt it all, let's hide it all, let's sign our signals, let's sign our messages. So we just sign, okay, I am the beacon coming from this base station, and here's my signature, right? The node that's receiving this can verify that the signature is correct, right? So that should be fine. That should be enough. Well, this is clearly not enough, right? Because all these traditional security primitives don't help here, because the attacker didn't really try to modify this message. He didn't try to modify the content of the message. He didn't try to modify what is written in the message sent by the base station. It simply modifies some properties that you measure, the properties of the signal that you measure in order to obtain your location. So it's violating another type of integrity, the integrity of the time of signal arrival, the integrity of the signal characteristics, and it can also introduce or remove signals from the channel. So we are dealing with a completely different adversary than what we were used to in traditional security, where we talk about the content of messages, where we talk about the content of digital data that is being communicated. So we need something else. So I'll present a system which we recently published this year at Mobicom. It's called SatNav, and it's secure localization or secure navigation, secure broadcast navigation system. So what was the goal of this secure navigation system? Well, we wanted to compute the correct location of a trusted device in the presence of an attacker. So we have a device, B. We have some base stations that we can set up on a campus. And we want to make sure that B cannot be cheated on his location by an external attacker. That's what we want to do. So we want to prevent all these attacks that I talked about earlier. So what are our assumptions? Well, our assumptions are the following, right? We assume that we have an infrastructure of base stations which can be transmitting on different channels. So they transmit on different radio channels using different bands that are covering a certain area, like a university campus, a Purdue University campus. We have a node, the user, that is aware that it is in the campus but doesn't know where it is in the campus. So he knows that he is on campus, but he doesn't know where on campus. And we assume that the attacker can deploy as many stations as he wishes. He can replay, delay, jam, whatever he wants, right? So he can deploy a number of rogue stations wherever he wants. And we want to prevent the attacks that I mentioned. So this requirement here is crucial for this scheme. I'll remove this requirement in some other schemes, but the user has to be aware of its presence in the coverage area, and you'll see why. So he has to know at least that he's on campus. So how does this work? Well, the way that this works is that we are going to send simple, non-encrypted, non-signed beacons from the base stations to the node. So these base stations are going to send beacons which will contain, for example, if we want to have this beacon-based localization, will contain simply, I'm station number 1, and this is the time at which I send my beacon. So just a plain timestamp on a given frequency, right, on a given channel, and we just send that. Please notice that B doesn't share any keys with the base station. Doesn't know the public keys of the base station. He only knows that there is a legitimate infrastructure on site, and it is going to transmit on these channels. That's a pretty simple assumption, right? So, since the beacons are not signed or encrypted, what do we do in order to prevent that these beacons are now overwritten or simply blocked and replaced by fake beacons? What do we do? Well, this is what we do. We call it integrity coding, and it's a pretty interesting scheme which does the following. So you take a beacon, you take this message which will be sent by the base station, and this is a string of ones and zeros, right? It's a message that you generate. What you do is you expand this message using, for example, Manchester coding, such that each one will be converted into 1, 0, and each 0 will be converted into 0, 1. That's very simple. For any message, you will obtain a corresponding message, which now has a very interesting property for us. And that is that it contains exactly the same number of ones and zeros. So for whatever you put here, you get a message that contains an equal number of ones and zeros. So the humming weight, half of the length. And then what you do is you take this message, and then so this is what is done by the base station. You generate a random signal within your frequency band, which is transmitted when 1 is supposed to be transmitted. So it's just the presence of a random signal on the channel. This is what the base station does. It simply takes a 1 and simply transmits something random on the channel. Well, when it wants to transmit a 0, it doesn't transmit. It just says, well, I keep quiet. And the base station keeps on transmitting this all the time. So when the infrastructure is on, the base station just simply transmits this all the time. So this is a kind of unidirectional coding that we do here. So we do some Manchester coding with on-off keying, and we generate these random signals. So now, when we have a receiver, so when we have a receiver receiving this signal, what happens now? Well, we take a very simple threshold-based scheme, right? The receiver sees some signals on the channel. If there is a signal on the channel, it converts it interprets this as a 1. If there is no signal below a certain threshold, it simply says, well, this is a 0. And just keep in mind that here we are not measuring signals to noise ratios or whatever. We just measure the pure energy of the signal on the channel. So what you receive in your antenna, you just register, okay, within this frequency band, I received a certain level of energy, right? And then after you decode this from a signal to the message, what the receiver simply has to check is, does this message contain the same number of ones and zeros? If it contains the same number of ones and zeros, it's a legitimate message. It hasn't been overridden. It hasn't been modified by the attacker in any way. This is the channel. You keep it always busy with such signals, right? Why is this the case? Well, this is why. Because if a base station is sending this on the channel, right? This is a message containing the same number of ones and zeros. If the attacker inserts a signal where a 0 should appear, then the number of ones and zeros will be changed in this message. So at the end, the receiver will notice that now there are more ones than zeros, meaning that the integrity of this message was modified. Doesn't hold, essentially. But if the attacker tries to cancel out this 1 into a 0, he will run into a lot of trouble. I mean, canceling out a random signal on a channel is a non-trivial task. So if you randomize this sufficiently within your band that you can afford, either by changing the phase or by whatever you might think of, you have a pretty good. I mean, the attacker has a pretty difficult job in order to cancel out this signal. So now this job of canceling out the signal. So if you just look. So we call it an anti-blocking property of the wireless channel. Why? Because, well, if you send this kind of information on a wireless channel, you can, to actually subtract the energy from the channel, What you have to do, you have to estimate the phase of your signal at the receiver. And this phase will change if you misestimated the distance, if there are reflections, it's practically almost impossible to cancel out, right? And the wider your channel that you work on, obviously the task is more difficult for the attacker. So what we have here is a primitive which allows us to protect the integrity of our message on the channel. So whatever the base station sends, the attacker cannot he can modify it, but not without the receiver noticing the modification. And we didn't use any keys. We just used publicly available channels. We just said, well, on this channel, in this space, there is a transmitter which is trusted. There might be 10 other untrusted transmitters around. You don't care. So in order to show how this can be done, well, what you can do is if you have a 1 and if you want to send a truly random signal, you can simply change the phase, and then you can compute what is the probability that the attacker can attenuate your signal within a given. So you can make this as fine-grained as you want, depending on your system, on your frequencies, and so on. So there are some things that can be tested here, how an attacker could do early detection and then try to invert, but these are very, very sophisticated. These might turn out to be extremely difficult tasks to do. So, we essentially also came up with, if your navigation messages are not of a fixed length, if you want to send some other information, well, you can also use we call them delimiters, which are some delimiters that you use for synchronization, which have a specific property that they can never be turned into a part of the message, and therefore you can use them as delimiters for your messages. And using this, you can recover your signals between the delimiters. So this is kind of a building block that we proposed in 2006 that we used. We kind of went in with an idea of how can we do broadcast authentication or integrity verification without using any signatures or any keys, MACs, distribution, or whatever. The only public information we need are the channels. So this gives you a very nice property, meaning that if you know that there is an access point here on campus transmitting on channel 5 all the time, if it transmits, for example, a public key of a network, then you will always, whenever you come to Purdue, you turn on your computer, you switch to channel 5, you will either receive a legitimate public key or junk. And you can count on that. So this was the idea that we used here. But now, how can this be used for secure navigation? Well, the answer is simple. It's almost straightforward. What we can do is we can now take any navigation message, either in a GPS-like system, which is based on time of arrival, and send it using this scheme, using integrity coding. Well, what happens then? Or we can use a beacon-based scheme. Well, what happens here? Well, you essentially prevented any time shifts of the navigation messages, because in order for the attacker to simply take a message that appeared in the past and replay it at another time, since you are constantly transmitting, they will mutually add up, and the integrity of the messages will be violated, and as a receiver you will notice that something is wrong. So you again have this integrity property, and the attacker cannot shift your messages in time. You can do it either with beacon-based or with time of arrival or time difference of arrival-based schemes. Well, given that time of arrival and time difference of arrival schemes are a bit involved to implement, we did an implementation using 802.11. So on one side we had a regular laptop with a wireless card, and we had a receiver which was a software radio, just in order to be able to observe in a bit more fine-grained way what's happening on the channel. And this is what we got. At first we thought, these were the measurements done at the ETH campus. So at first we thought, well, you know, the noise will be so high, and then, you know, if you have these channels, maybe it will not work out. But surprisingly, it worked like a charm. These are ones and zeros, right? And they're, as you can see, I mean, they're very easy to distinguish. Even up to 70, 90 meters, you can fairly nicely distinguish between background noise and your signal. So it only depends on how you tune your signal, your system. Obviously, if someone interferes here, he will kill your system. But well, you can do, since the beacons are being transmitted all the time, you can definitely, for occasional interference, you're pretty fine. So we ran into some issues of how to do coverage, right? I mean, if you have a wider area, and if you want to cover this wider area with some channels, then, you know, two beacons transmitting on the same channel may mutually, two base stations transmitting on the same channel will mutually interfere. So we can come up with a certain scheme that we have full coverage with 7 channels where there will be no mutual interference, or better said, it will be fairly minimal interference. These numbers give you the channels that we use from each of these base stations, and with a bit of thinking, you will end up seeing why this works out so nicely. Also, in terms of how fast can you go here, well, it really depends on your equipment. But using what we are using here with 802.11 based implementation, 500 bits per second, which is perfectly fine for a navigation signal. But then we also had, I don't know if I have the slides on that, but we had a custom-built device, a custom-built pair of devices doing this integrity coding and doing this navigation, and we transmitted at 20 kilobits per second. So it depends how fast you are, how narrow your signals can be, and so on. And you can play with this in terms of robustness. How narrow do you want your system to be, and so forth. You can also do various optimizations. So, for example, you can transmit only so if this is your original message, you can transmit it over a normal high bandwidth signal, high bandwidth channel. And then you can simply transmit a digest, like a hash, of your navigation message using integrity coding. Because then you need to transmit only 160 bits, and your message can be as long as you want it to be. So what does SatNav really give you? Well, it gives you secure broadcast localization. It also gives you secure broadcast time synchronization. I didn't go into that too much. And it can be implemented on a number of legacy systems. Also, it can equally work on time of arrival or time difference of arrival systems. We haven't implemented that yet, but we are working on that. So, and an application of this is, you know, you can generally use it on a campus. You can use it in any confined area where you have some awareness that you are within an area of interest. That within this area there is a secure navigation system up and running, and then you can turn on your device and say, okay, now I'm here within this area. It can be a city as well if you set up such an infrastructure within that city. By the way, this requirement, if you think about it, is not that strange, because almost the same requirement holds for GPS. If there is no GPS coverage in this room, I can feed you with whatever I want, and you will pretty much buy my location. So these 3 dots there stand for more, for those who want to know more, right? We didn't stop here. I mean, this was actually just one of our latest projects. We did a lot more earlier on a slightly different problem, which is if I have a device which maybe has a correctly computed location, it knows where it is, but wants to lie. So wants to tell me that it's somewhere else. What do I do? I mean, how do I know that this guy here is that this P prime is equal to P? Maybe it's something else. Maybe it's a different location. Because an attacker might have some incentives like access control or whatever else to claim that it's somewhere else. It's not that it doesn't want to tell you where it is. It wants to claim that it's somewhere else. Because if it doesn't want to tell you where it is, well, pretty much there's nothing that you can do. But if it stands to gain some benefit from lying to you where it is, then you want a way to verify. So how does a base station know that it's getting a correctly reported location? Here we did a lot of work, and I must say that surprisingly, one of the first papers that tackled with this kind of problems was a paper on proximity detection by Brands and Chaum. It was a distance bounding protocol, which wanted to verify whether a card was close to an ATM. Whether you are talking to whether the ATM that you are talking to is a legitimate ATM and not maybe a fake ATM that's kind of routing your messages to a correct ATM. We turned it into a wireless protocol, adding some, let's say, mildly modifying what Brands and Chaum did. There were also some other modifications by Markus Kuhn and by the group of Dave Wagner at Berkeley. But what is the main idea here? Well, the main idea is very simple. To create an efficient protocol by which I can upper bound the distance to a device. By upper bound, what I mean is that if this is a base station, that this node A cannot pretend to be closer than it actually is. It can only pretend to be further. So you can challenge him and it's supposed to reply in a given time. You can devise some clever way of doing that such that the processing time at the node is minimized. So what you do is you challenge him. The only thing that he can do is he can delay his reply. He cannot reply faster than he receives your original message. So here, what you get is a very nice primitive that enables you to upper bound this device. But then you have to be a bit clever because this guy can always claim to be further, so what's the use? Well, now surprisingly, if you put this in a triangle, so if you use 3 or 4 in 3D base stations, and you form a certain, what we call a verification triangle, then what you can do is you can use the following feature, which is that if this node is trying to lie and it's trying to enlarge its distance to base station 1, well, it will necessarily reduce its distance to one of the remaining 2, and you will detect that it's trying to lie. So if you do this, you have a perfect location verification system, which has the following property, which is that within the verification triangle, that a device cannot pretend to be at a different location. Additionally, if a device is somewhere outside of the triangle, it cannot pretend to be within the triangle. So you have a location verification scheme that you can use for an access control. And we are very close to finalizing the implementation of this scheme. So more results will follow on this. We call this verifiable multilateration, and it's resistant both to internal attacks, so you can do location verification, but it's also quite resilient to external attacks as well. So you can do things a bit more. You can do more in terms of location verification. You don't need to form triangles, for example. What you can do is you can hide your infrastructure. You can simply hide it. How? Well, it's a very simple idea. If I am hidden as an infrastructure and you are transmitting certain messages to me, for example, you are sending me a signal, and based on the signal decay, I'm supposed to see what is my distance to you. Well, now you can always say I send at power p, and instead you send at power p prime. So I would get a wrong estimate of the distance, and what can I do to prevent that? Well, what I can do, I can ask you to tell me your location, and then ask you to send me your message, and to tell me at which power level you sent it. Now, if the reported location, which is here, PF, a fake location, doesn't correspond, so if the distance to the reported location doesn't correspond to the distance that I obtained that you tried to fake, then you are lying. And this works under the assumption that I hide. Okay, so I'm somewhere in the hidden, somewhere in the bushes, right? Trying to verify where you are. Putting this in a mobile scenario, you have an excellent scheme because nodes move all the time, and tracking where someone is very, very hard. So we developed a set of protocols that can deal with that and that can benefit from that. And this is just to give you an idea about some additional work on secure localization and location verification that can be done. Now, coming to the kind of second line in my title, which was location awareness. How can we benefit from location awareness in order to provide some basic security primitives? As we showed already, using integrity codes, what we use is presence awareness. So I'm aware that I'm in a power range of an infrastructure which is transmitting on this campus, so I know that I'm covered by the infrastructure. I use presence awareness, and what I get is authenticity and integrity. So out of location information, or basically out of the knowledge about the location, awareness of location, I'm getting some strong security primitives, if you want, right? Well, once that you start thinking about presence awareness, then you might also start thinking about absence awareness. So we showed in a different work that if you know that the attacker is outside of a certain region, and here this region we call it an integrity region, which is marked by these two circles. If you know that the attacker is not within this the union of these two spheres, then you know that you can safely establish a key between these two devices without any danger of a man-in-the-middle attack. And here we use some ranging protocols using ultrasonic ranging, and you can be 100% sure. So you take two devices, A and B, you put them together, and you can visually see, that there are no attackers around them in these circles, right? In these spheres. And you press two buttons and they are paired. So you are putting a lot of pressure on the attacker, because if he wants to evade such a protocol, he physically has to be in an integrity region. Even if this region is a bit bigger, you are still forcing him to be on the site. He can no longer have a very high power directional antenna and sitting at home aiming at your devices. He has to come inside, or he has to get close to you, which is much more difficult. We are not alone here, so we were not the only ones doing this work. So here in these slides that you can, I guess, download online, you can find a number of papers that relate to distance verification, which mainly deal with distance bounding or authenticating ranging protocols, secure localization and location verification papers. I have to mention the work of Lukas Lazos and Rada Puvendran, also Markus Kuhn, and other works, for example, those dealing with secure localization in multi-hop networks, where you can leverage on some redundancy to detect if someone is trying to lie about location, secure time synchronization, and so on. So, in conclusion, what we have is something like emerging electronic warfare in civilian applications. So wireless electronic warfare is kind of moving to civilian applications, and we have to rethink what we do. I mean, traditionally this topic was in the military domain, and we didn't care that much because it didn't impact us so much. The same thing happened with the internet. So here as well, we are now facing this because there will be many of these devices around us. And the location information and time information is crucial there. Imagine a sensor network or a single sensor sending you one information, 20 degrees Celsius. What is the question that you want to ask? Where and when? These are the two questions that you will always ask. Whenever someone tells you there is an accident or there is an event, what you will ask yourself is where and when. And these are the two things that you absolutely want to protect if you want to have any reliable information. And on top of that, location awareness or awareness of the absence or presence of certain devices in a certain area can help you a lot. So you can leverage on location information. Equally, I didn't mention it here because there's no time. You can build much more efficient security protocols on top of secure time synchronization, for example. If you have time, you are really, really in a good starting state. All your broadcast authentication protocols, they will all benefit hugely. You usually need at least half. I mean, you need half of the messages that you would usually transmit. So you can use timestamps and so forth. And for the end, I just put some publications that relate to this talk. So on SatNav, on integrity coding, on location verification, and on device pairing protocols. We have a catchy website on securelocalization.com, which for now doesn't do much but reroute you to our web pages. But hopefully it will contain a much more detailed description of all the existing schemes, not only ours, in that field. And this is my email if you want to contact me. And I hope I think I'm pretty much on time. And if you have any questions, I'll be more than happy to answer them. So thank you.
I'm just curious that can you tell me what's the accuracy of using a signal strength to estimate the distance?
So the accuracy of using signal strength to estimate the distance is extremely low. I mean, if you use RSS-based localization or ranging, then you will hit many problems. Even depending on if your antenna is facing down or up, or if your node is so it's extremely tough. Many researchers have shown that, and I think you can use it only for some coarse-grained localization. So probably the best that you can do in those scenarios would be something like beacon-based localization, so range-free localization. You can obviously benefit if you use some RSS-based space fingerprinting, so you can fingerprint spaces, but that's not something that we looked at here. Related to SatNav, for example, for us, this beacon-based or range-free was only one example of how we can simply implement it. Those schemes are very appealing because they are simple to use, but they are not very good. Yeah?
A couple of comments. Your talk was excellent. Really understood.
Thank you.
We tried to do some work in providing privacy, which means we don't want people to know exactly where we are, when did we send the signal, and all those things. And we use the geometry. There's a paper in Transactional Mobile Computing. I was just wondering, is there any way we can provide somebody who doesn't want to tell anything, but want to participate, doesn't want to tell about the location? Is there any way you could protect his privacy?
Okay, so first of all, we are working on it. We have two projects that are kind of competing, and that's a funny story. We have a project also on device identification, trying to invade privacy, and then we have a project within this project on secure localization. We have efforts to provide location privacy. Is there a way? Well, if your system is based on location, on awareness of location or proving certain location, then it's extremely hard. Equally, from my past experiences with devices which you can, I think we discussed it already, so which you can fingerprint, so you can actually extract a fingerprint of a sensor, of a node, of a radio. So each radio is kind of unique, so when it transmits, it gives you a unique fingerprint. So you can even do that, right? You can set up an infrastructure that for any message that you send will do time difference of arrival or RSSI-based measurements, and will try to infer where you are. Now, trying to hide location information, I it's a very, very hard problem. I don't have a solution for it, and I would love to hear someone who has, but I don't think it will come that soon. I think it's a very, very difficult problem. Maybe in a multi-hop scenario where you can leverage on some information hiding, some mixing that can work partially within a given locality, but it's a very tough problem. If the attacker is assumed to be omnipresent, it's a very tough problem.
But what I'm realizing is that you're making it very difficult.
Among other things, yes. Yes?
I have a couple of questions. If you assume that there's time synchronization, let's say between satellite and the GPS receivers somehow, then a simple solution where like the satellite signs everything would be enough?
Okay, so if you assume that there is time synchronization between the satellite and the devices, then you are then you are in a slightly better position, okay, because you are still measuring time. Okay, so you are still measuring time of flight, which can be delayed by the attackers, right? So you are still going back. So there, the solution of using verifiable multilateration still applies. So you still need something like this, right? If you have an external.
I was actually referring to the secure navigation, to the first problem.
Okay. Yeah, yeah. So if you have a secure time synchronization there, so what you are saying is that you would send signed messages that could be overshadowed by the attacker. Very simple, right?
Okay, but I guess in this system you also assume that the attacker cannot jam those beacons.
No, he can jam, but it's just that then a whole bunch of ones will appear on your device, and you will know that the messages are.
He cannot jam and just broadcast his own beacon, for example?
No, because your beacons are constantly being the legitimate beacons are constantly being sent, right? So at your receiver you will receive both the legitimate beacons and the attacker's beacons. And the only thing that the attacker can do is either amplify your ones or turn zeros into ones. So he cannot do much. I mean, because jamming doesn't happen at the sender, it happens at the receiver, right? So unless he wraps a foil around the receiver, I think you are perfectly fine. Yeah.
I think you also made future security issues much easier by getting control of this problem.
That's what we are kind of hoping to achieve, to provide basic primitives for future networking functions. For example, if you want to do secure routing, then knowing location securely certainly helps, right? Having time synchronization will reduce your overheads. Knowing location securely will, and also verifying location securely will help you with any broadcast, with any multicast, with any aggregation, with compromise detection. I mean, provides you. So the main idea here, when I go back when we started, was, well, let's wire the wireless networks. Let's have the topology on top of the wireless networks, because what you have in the internet that's pretty much what you have, kind of, right? You have routers, you have certain hierarchy, so you kind of know where people are, where that device is. You can sort of trace it, right? It has a certain structure. Here there's no structure, so you want to ground it. You want to know where they are, and when you know where they are, it's much more easier to detect who's doing what and how to prevent it then.
So these problems are not in the internet.
Well, these problems are. Okay, so there were some works, there were some projects and papers that are trying to tackle, where a node is when you communicate online. Where is this node geographically? If there is no IP spoofing and so on, then you can pretty much hit where he is. You can do some tracebacks and so on, but it's a much more rigid rigid topology than this is, right? So here we wanted to provide that, at least some level of assurance where the nodes are. It also then can help you enforce a lot of accountability. You know where someone was, you know where, so you can assume what he did there, and if there was some damage done there. A very simple scenario is you have a car crash in future vehicular networks, and someone flees the scene of crime, right? Then you can use, so if you do secure localization or some distance bounding, you can always leverage on the information that someone was there. Because while he was in legitimate state, he would report certain locations, and you can verify that he was close or far. And there are incentives for doing that, so you can go back and trace who was there, and not only trace who was there, you can prove that he was there, which is more important for any kind of liability issues and so forth.
It becomes very fundamental.
Yeah.
Should we do something informal then? Thank our speaker.